Okay, people, we better get started. We are having today the third lecture, the third and the last lecture on introductory courses on neutrinos. As of yesterday, please feel free to interrupt me anytime if you have any question. Okay, so yesterday we start seeing what we can find that we are not expecting in the long baseline program, essentially. Of course, you have dedicated lectures of Beyond the Standard Model with Neutrinos. Stefan will cover more UV complete theories. I'm going to show what is not UV complete theories, what can be really radically different. So in this sense, the overlap is zero. This is completely different kind of physics. So yesterday we saw what happens with sterile neutrinos and what would happen if you have unitarity violations. And we are going to become a little bit more radical now and talk about non-standard neutrino interactions. Non-standard neutrino interactions, of course, are not any interaction you can dream of that is not contained in the standard model. It's far from being that. It's just those interactions that can be written in the form of this four Fermi Hamiltonian, where I have factored out a G Fermi for you to see that this epsilon parameterizes how strong or how weak my interactions are compared to the already weak interactions. But of course, we know nothing about the non-standard neutrino interaction that can happen at any time. So if I'm really interested in finding these non-standard neutrino interactions, I have to break down the analysis into non-standard neutrino interactions at production, at the time evolution of my neutrino, and non-standard interactions at the detection of my neutrinos. However, these non-standard neutrino interactions at the production and at the detection point involve a charged lepton. And they have been bounded, for example, in meson decays and in other places as well. And the bound puts the epsilons in, let's say, 10 to the minus 2, 10 to the minus 3, depending exactly on the channel, but they are completely uninteresting from the point of view of the long baseline experiments. For the point of view of the long baseline experiments, you are left only with what are called neutral current non-standard neutrino interactions, meaning you have two neutrinos on this leg. And these non-standard neutrino interactions can be incorporated into the effective Hamiltonian, which we use to describe oscillations in this way. And this should really look familiar for you, especially if I put word eighth there, because we are incorporating them exactly in the same way we incorporated yesterday in matter effects. This non-standard interaction can be thought of as a kind of matter effects. It's neutrino propagating in a medium. This is not exactly a good analogy, but you can start thinking about that. If you go as we are doing to understand, a Cantor picture of that in just two flavors, this is the expression you get. And as we have said yesterday, we can remove from the Hamiltonian anything proportional to the identity matrix. So without any loss of generality, I can take this term to be zero, and this will be the difference of the two. And losing some generality, but life is the way it is, we are going to take the off-diagonal parameter to be real in such a way that all the non-standard neutrino interactions can be described by two parameters, the diagonal parameter and the off-diagonal parameter. Now, let's see how I'm going to find that. For this, let's remind ourselves how these experiments. Because you have matter effects. Neutrinos are propagated on the Earth. So you have the standard matter effects because neutrinos, I am assuming neutrinos are propagated on the Earth. So they are already propagated in the Earth. On top of the matter effects, they have these new interactions, okay? So this is muon neutrino survival probability, and you look for the probability, the survival probability. So we know that the depth of this dip, the amplitude of the oscillation, from the amplitude of the oscillation, you extract the mixing angle. Remember that. Now, the position of the minimum is where the kinematic phase becomes 1. This means I extract from there the value of the mass. Now, what would happen if I include non-standard neutrino interactions? Well, the off-diagonal term modifies the survival probability at very large energies. This means this change the position of the mass. This shifts the determination of the mass. Again, this behaves as matter effects. So it changes the determination of the mass, one side for neutrinos and the opposite side for the antineutrinos. It breaks the degeneracy, okay? And what happens with the diagonal term, it changes the oscillation probability near the first minimum. This means it changes the extraction, the determination of the mixing angle. Again, if it enlarges it for neutrinos, it suppresses it for antineutrinos, or the other way around. Now, let me put this aside and become really, really radical. I'm going to talk about CPT violation. Nobody ever talks about CPT violation, and the reason is clear, because we have a theorem, which is the CPT theorem, which states that any local quantum relativistic field theory with respect to Lorentz invariance automatically has CPT built in. So CPT is a sacred cow of the standard model. Why? Because it's based on nothing. It's based on hermeticity, locality, and Lorentz invariance, which are all ingredients we put in our theory for other reasons than to keep CPT. So what we are going to do that now is to chop a sacred cow into a hamburger and see what happens if we assume, just for the sake of it. Okay, I worked a lot on this. I would be happy to talk how you implement this in the quantum field language, okay? But I mean, we don't have time. For the sake of my talk, I'm going to assume that just for the sake of it, neutrinos and antineutrinos can have different masses and different mixing angles. But even if you are willing to do that, someone will come and show you this bound. This bound is in the PDG and is called the most stringent relative bound on CPT. Violation comes from the kaon system. We talked yesterday about kaons. This is a bound from the 80s, from the CP-Lear experiment. Okay, so if you look at this bound, you feel a little bit, scared. There seems to be no room for CPT violation, but this bound is very deceiving if you look at it enough. Of course, we like dimensionless quantities because dimensionless quantities convey a message. However, if CPT is violated at all in nature, the scale at which this happens has nothing to do with the average mass of the count, the denominator. You could have gotten a much stronger bound, 19 orders of magnitude stronger bound, if instead of putting the average mass of the count, you have put en Planck, or my mass, for that matter, equally meaningless, okay? So unless you have a scale to which attached to the phenomenon, there is no point in adimensionalizing your bound. So you have to restore the units. It's even more problematic than that. Okay, the kaons are not elementary particles, and we already know that its mass is not given by its constituents, but by QCD. So whatever this bound is testing, if anything, has nothing to do with CPT violation in elementary particles, okay? So if you start by restoring the units to this bound, you multiply both sides by the average mass of the kaon, and this is the way the bound looks like. It really looks in a way we look at neutrinos, but besides that, it's the correct way of looking at the bound of kaons, because a kaon is a boson, and the parameter entering Lagrangian for a boson is the mass square, not the mass. So if you put the bound in this way, the bound is laughingstock. It's not a serious bound any longer. We already know that with neutrinos, we can already improve this bound by several orders of magnitude. But of course, counts are not the only game in town. We have been doing CPT tests for the last 20 years. This is the collection of all the tests we have done, collected by Eberhard Wittmann a couple of years ago. I'm going to talk about the orange lines later. Let me talk about the blue lines now. You can see the blue lines, it's the relative bounds. The count is the strongest one. But once you look at these bounds, you realize immediately that they either involve non-elementary particles, proton and antiproton, hydrogen, what do you mean? Or they involve elementary particles with charge contamination, like the electron, and we already know about the electromagnetic contribution to the mass. So if you want to test CPT violation in elementary particle system with no contaminations, this means you have to do it with neutrinos. There is no other way out. You have no choice. Okay, so, and it's even nicer than that. It's already done. The only thing you need to do is to sort out which experiments involve neutrinos and which experiments involve antineutrinos. So you already know that solar neutrinos involve only neutrinos. Reactor neutrinos involve antineutrinos, and short and long baseline experiments, they run in neutrino and antineutrino mode separately. It cannot be easier. Okay, the problem is the little detail is you have to throw away 40 years of atmospheric data, because in the atmospheric case, they cannot tell neutrinos and antineutrinos on an event by event basis. Okay, so you remember where you extracted each quantity and you do the fit. And this is what you get. This is the math. This is the most stringent bound you have on CPT violation in neutrinos. So you see that there is plenty of room for CPT violations still in the mixing angles. But there is something way more interesting than there. If you look at the atmospheric mass difference, you see that, as you expect, is 1 order of magnitude below the baseline mass. Go ahead. Yes. I can talk about this later. Yes, if you find CPT violation, what could happen? I will talk about this briefly, but we can talk about this more. This is experimental bounds. Okay, so you see that this mass, the difference, is 1 order of magnitude below the baseline mass, 10 to the minus 3. However, something strong is going on, something very fishy is going on in the solar case, where you are exactly in the same ballpark as the mass itself. Okay, so the bound, the bound is larger than the best determination of the solar mass difference itself. And the reason is because there is some tension, although I haven't mentioned this explicitly yesterday, between solar determinations of the mass and Kamlan determination of the mass involving antineutrinos. And this is not a matter of tuning parameters. There is a physical reason behind that. Super K is seeing a day-night asymmetry. And if you see a significant day-night asymmetry, this pulls your mass down. Okay, you cannot go up. So there is a reason why this tension is there, a physical reason why this tension is there. What is this? Here you have 1, 2, and 3 sigma determinations for the mass difference and the mixing angle using solar neutrinos, and this is Kamlan. These are the standard values. This is 7, 10 to the minus 5. This is 3 times something, 10 to the minus 5. Okay, so luckily for all of us, the new generation of experiments will sort this out completely. Juno is to be completed this year. We'll run with antineutrinos. We'll make this determination, and of course, due to hypercase. So the situation is nice already. But can we say already something? There are experiments that I will be very brief because I don't have time to cover that, but only 2 collaborations have done the separate analysis neutrinos and antineutrinos. This is T2K and the MINOS collaboration. And these are MINOS and T2K results. Okay, do not hold your breath. Of course, everything is consistent with CPT conservation. Although they look different, this is because the T2K collaboration does it as it should, sine square of theta, but MINOS does it at sine square of 2 theta. This is why they fold the regions, and you don't see that. But the important thing, the thing which is important to notice here is that although there is some room for CPT violation, this is not the important point really. The important point is here you have black. In black line is what you see for antineutrinos. In blue, what you see for neutrinos. The regions, because of production, you have 1/3 of the antineutrinos compared to the neutrinos. This is where the regions are wider when you use antineutrinos. But the important thing to notice, you can even notice it by eye, is that this is in pink, the combined fit. The combined fit is farther away from both the neutrino and the antineutrino signal, and you realize immediately what we are doing wrong here. We are assuming, to get the best fit points, that neutrinos and that CPT is conserved without testing it, and we can get fake solutions. This is something I'm going to say very, very briefly, but the idea is that in experiments today, you do a combined fit. You put your neutrino and antineutrino data, and just because of statistics, if you want to go a competitive fit, neutrinos and antineutrinos, you have to run, roughly speaking, 3 more times in the antineutrino mode than in the neutrino mode to compensate for statistics. And this is money. This is just the reason why we are not doing that. There is no other reason than that. So we assume that CPT is conserved and make a combined fit. And you will understand immediately what might be going on. Just imagine all the features of neutrino is driven by 1 parameter. 1 parameter in neutrino and 1 parameter in the antineutrino. So there you are. When you minimize your likelihood You get a minimum for the neutrino sector and a minimum for the antineutrino sector. Now, if you assume that CPT is conserved, you are assuming that it's the same parameter in the neutrino and the antineutrino sector, and of course you recover the minimum you have obtained before, but you get a new, an impostor solution that can maybe even deeper than the other two. So you can be running in impostor solutions. If you take, for example, what was done in T2K best fit, okay, and you improve this, you assume that they are going to run way more years as they are going to do, you can see that the combined fit excludes the real values in neutrinos and antineutrinos. I'm taking the best fit points they have used in the previous run face value. You exclude the true values and 3 and 5 sigma. You can have way more problems than that. The situation is more problematic than that. I'm not going to enter into details, but you would have to define how can you, if CPT is violated, how is the refacing done again? Remember that we counted yesterday how many parameter phases can be removed away if, okay, by redefining the fields. You cannot play this game if CPT is violated, at least not in the same way. So the counting of phases is different if CPT is violated. But even worse than that, we have seen yesterday a version of this plot. Not exactly this plot, but we have seen a version of this plot. This is the plot people use to claim that CP conservation has been ruled out at 3 sigma. Okay, there you are the T2K result in blue, the NOVA result in red, and the global fit in green, and you see that this delta chi-square is more than 9, so you are saying that CP0, phase of 0 is ruled out at 3 sigma. However, these plots assume CPT conservation. If you let the mixing angle to be slightly different in the neutrino and the antineutrino channel, all the values are allowed at 1 sigma. You have to be very, very careful. You are trying to make a very strong claim that CP is violated. However, you haven't tested yet CPT to the same level. So the precision we are reaching is such that we don't want to run into an impostor solution. And impostor solutions, I show you, do exist. You have to be very, very careful with that. Now, I told you before that we have non-standard neutrino interactions, and now I'm talking about CPT violation. Both apparently have the same trademark, which is different masses and different mixing angles in neutrino and antineutrino sector. So imagine at some point one day, I run an experiment, I find different masses and mixing angles for neutrinos and antineutrinos. How can I know? How can I tell? It's just a non-standard neutrino interaction, an interaction that can be at least effectively incorporated into the standard model in some way, or it's just a true CPT violation, a violation that challenges our description of nature in terms of local relativistic quantum field theories, at least to some extent. Should I be able to do that? Of course you are. Just imagine for most of the parameter space. Just imagine you run your experiment, neutrino, antineutrino mode, you get 2 mass difference and 2 mixing angles, okay? One for the neutrinos and one for the neutrinos. Then the only thing you have to do, I'm again showing this, what happens in the 2 flavor case. The 3 flavor case, you can do the same game, but it's numerically more complicated. You invert the problem and you express the Bayer masses and the Bayer mixing angle and the strengths of the non-standard interaction as the function of the parameters you are obtaining. And of course, the first thing you try is non-standard interactions, but you can see that for most of the parameter space, both signals can be really, really different. You can differentiate both. Of course, there are regions of the parameter space where you can. So I'm going to move quickly to the last signature of physics beyond the standard model I'm going to talk about, which is violation of Lorentz invariance. Violations of Lorentz invariance should be incorporated also in the Hamiltonian formalism. They don't have and quantum field theory analog, and they can be incorporated in this way, where this is the standard Lorentz covariant form term, the one we have been using so far. These A's and C's are called standard model effective coefficients and are the orange lines I showed you before in the plot of CPT. So these A terms are, you can see by comparison with the Lorentz covariant term, these are dimension-full terms and are like a vector acquiring a web. And this term violates both CPT and Lorentz invariance. The C terms are like tensors acquiring a web. They are dimensionless, and they violate only Lorentz invariance. And of course, you can put new terms with more and more and more Lorentz indices. The rule of thumb is if it has an odd number of Lorentz indices, it violates both CPT and Lorentz invariant. It has an even number of Lorentz indices, it violates only Lorentz invariance. And you realize immediately why I separated before CPT violation in the masses from this term, because a mass term has 0 Lorentz indices. It has no way of finding a way in this description. And as you think that this is going to be a mess, but in fact it's not, because nature is generous, and the kinematic phase in oscillation is still the difference on the effective eigenvalues of the Hamiltonian in this way. So although I cannot get by hand the expressions, I can see how they will behave with the energy and the baseline length. The spectral distortions are easy to see. The only thing I need to know is that this term, and we worked this out, has spectral distortions all L over E. We have seen this yesterday. This is the standard Lorentz covariant term. So this term, which violates CPT and Lorentz invariance, has an energy on the denominator on top of the energy of the numerator, so you know it won't have an energy dependent. It will scale only with the baseline. These terms have 2 powers of energies in the numerator on top of the one in the denominator, so this term scales like L times E and not L over E. So they bring a very strong spectral distortions, and you are sure you should be able to bound them or tell them apart if you want. So to see that, and this is the last time we are going to be the muon neutrino survival probability. This is the Lorentz covariant term we have seen many, many times. If I include this term only on top of this term, remember that this term is dimension-full and violates both CPT and Lorentz invariance. This is the kind of spectral distortions I expect. I have obtained this, I don't remember it by heart, but I have the mathematical notebook with me, with A's of the order of 10 to the minus 25 GeVs. If you include this term on top of the Lorentz covariant term, this term is dimensionless. These are the spectral distortions you get. I obtained that with C of 10 to the minus 31. So of course, if you put them both together, spectral distortions are huge, and therefore we have been able to effectively bound these terms to an amazing extent. And then, depending on the channel, 10 to the minus 31, 32, 34, and you can ask yourself when to stop, why I don't give up. I mean, my take on it, or I'm not doing that. My take on it is that we are just scratching the surface where we expect these terms to be. Nobody was expecting Lorentz violation of order 1. Okay, we expect them to be suppressed by M-Planck or M-Planck square. So we are just starting to see, to be sensitive to parameters where we expect them to be, not before that. Okay, so far we have been talking a lot about neutrinos mass differences. Let's talk about neutrino mass. I have shown you this plot many, many times, but I was very, very careful not to put anything on the y-axis. And the reason is because we have calculated that you can shift the spectrum up and down, and nothing will change with respect to neutrino oscillations. But there is a limit on how far you can shift this down. The lightest mass could be at most 0. It cannot go beyond that. So this means that I'm guaranteed that I will have one mass, which is the square root of the atmospheric of 50 milli-electron volt. Depending on the spectrum, I will have one mass of this order or 2 of them, okay, depending on the spectrum. So if you plot now the mass of the lightest neutrino square as a function of the three masses as a function of the mass square of the lightest neutrinos, you can see that if my neutrinos are kind of heavy or heavish, the 3 of them are degenerate. you don't care. The mass differences play no role. However, if my neutrino is light, the lightest neutrino is light, which is supposed to be, there is a huge difference on how the electron content is distributed in the two orderings. If I'm in normal ordering, 90% of the electron content, 95, is in the heavies, is in the lightest states. However, if my spectrum is heavy, 90%, 95 is on the heavy states. And why is this important? Because as we heard yesterday, we at some point entertained the idea that this game may end exactly as it started, measuring the beta decay, the spectrum of the electron emitted in beta decay. But why I'm so interested in measuring the spectrum of the electron emitted decay? I have measured it long time ago. I'm not interested in measuring the spectrum, but the endpoint, how the spectrum ends, not tracing the spectrum, just the tail of the spectrum. But the tail has its name tail for a reason, because there are no electrons there. Only 1 out of 10 to the 13 electrons set up there. This is why I need these huge experiments. I need tons of statistics to reproduce that. And why is this tail so important? Because if this is the shape of the decay rate, okay, if my neutrinos are degenerate in mass, the 3 masses are the same, you can take this square root out of the sum, and then this sum becomes 1 due to unitarity, and this is what you get. So the spectrum will tell is sensitive to the mass of the neutrinos. We saw this yesterday, and we have been chasing this mass for quite some time, okay, for 30 years. And the last of these is the Catherine experiment, which announced 2 weeks ago, a new determination of the mass, the sum of which is below 0.45, which is a factor of 2 better than the last determination. This is something like, 300 days of data. They will go over 1,000 days of data. This is the best determination, but they will reach a sensitivity of 0.2. Why are we not so excited about Catherine? Because I look for that. This is a slide I recovered for the first time I lectured for CERN, 2007, when Catherine was just a fantastic idea. At that time, the only bound on the masses of the neutrinos came from cosmology. We saw it yesterday in Yvonne. We didn't want the neutrinos to overclose the universe, and we put a mass. The sum of the masses should be below, let's say, 2 MeVs. This is what 1 MeV if you were very aggressive, but this was cosmology, and Catherine would be able to improve this bound 1 order of magnitude. This was very exciting at that time, but these experiments take a lot of time to build, and therefore, in the meantime, Planck already ruled it out all the space where Catherine is gonna see. We already are about to exclude these bounds, and of course, you are gonna say, I'm gonna say with you, that there is a lot of cooking in extracting these bounds for cosmology, and Yvonne will deal with that in all its gory details. I'm not going to enter into that, but the idea is that this bound essentially assume that relativity holds. That's it. That neutrinos have no other interactions but standard model interactions. This means, but however, let me say something. I work in non-standard neutrino interactions, in fact, with Yvonne, and we show that this is not going to be relaxed, this bound a lot, okay? And of course, it assumed that the universe reached thermal equilibrium, but the time of it reached MEVs. Let me say really briefly how these bounds are obtained, because Yvonne is going to cover this all. So you look at all the skies at the temperature, but you look at temperature as a field. You don't look at temperature as a number, so you expand it in spherical harmonics, okay, your field, and you calculate the power over each scale. And then you come up with this plot, okay, the CL's plot. It's just the Fourier transformation of this, and this plot is in initial conditions. You already know that. This plot has the geometry and the mass of the neutrinos. The first peak is sensitive to the mass of the neutrinos. This is why and then the second peak is the baryon asymmetry, and the remaining peaks are ineffective. Okay, but this is not by far the strongest determination we have for neutrinos. The strongest determination of the mass of the neutrinos, remember that in cosmology, I'm bounding my neutrinos gravitationally. This means I care only about the sum of the neutrino masses, okay? I don't care the flavors of neutrinos. I see them only as gravitational objects, so the sum of the three masses. In fact, I mean, so I'm not going to tell a little bit, I'm not going to tell much about that, but the strongest bound comes from structure formation. This is the strongest bound we have from neutrino, which is in fact very, very strong. Yvonne told the story yesterday. The universe emerged from a bang. Okay, after the bang, we have inflation. We believe inflation amplified the quantum fluctuations of dark matter to sizable level from 10 to the minus 19 to minus 5, which is what we need to make them seeds, okay? So, and you know what happens in perturbations. Yvonne will cover this in all details. I'm not interested about that. The equations of the perturbations are roughly speaking, a second order differential equations. If your universe is radiation dominated, remember my universe was very hot, was radiation dominated, it cooled off, it became matter dominated at some point. We saw it yesterday. So during radiation domination, this equation, the second order differential equation, the solutions, the exponentials are imaginary. Okay, you remember that the discriminant is negative, so they are imaginary solutions. If an imaginary solutions, perturbations just oscillate, don't do anything, okay? When you go to matter domination, this discriminant becomes positive. You have real exponents. This means you have growing and decaying mode, boom, your perturbation starts to grow, okay? At some point, your perturbations, the dense regions become more dense, the underdense regions, of course, become voids, and at some point, the overdense region gravitationally collapse and form bound objects. There you have, they start to get mass. So the key is who's going to contribute to this mass. Neutrinos, depending on whether they are relativistic or not, are going to free stream and puff up your mass, or are going to collapse and contribute to your mass. This depends on their wavelength compared to the scale of your object. So by tracing the power spectrum, the matter power spectrum, I can see whether, if you see neutrinos starting to contribute or not, whether neutrinos, what is the mass of the neutrinos. So this is the famous plot. You can see in the matter power spectrum the mass of your neutrinos. You can bound that. Okay, you are going to see this in full detail. I'm not going to enter into that, but the important thing that you cannot see is that these are the different bounds you can get from cosmology. If you use only Planck, this is the bound you can get, and it went until 0.09. I hope you can see that. I don't know how to switch off the light, so okay, anyway, what comes is not anymore this. So this is the bound you can get depending on the bounds you use. The situation changed a month and a half ago, 2 months ago, when DESI result appeared. DESI result lowered this bound a lot, but even became worse than that a month ago, where you cannot see that, of course, but there is 0.043. Using all the cosmological proofs, this is just a work using all the cosmological observables. I'm sorry you cannot see that, but it's 0.043. So 0.043 is a very bold statement, because we know that the sum of the neutrino masses is bounded to be larger than 0.059, 0.06, because we have seen the atmospheric mass difference. Okay, so this gets into trouble, but the mother of this problem is not the cosmological fit. This stands from Planck. This is a paper from Planck itself for 4 years ago. You can see that the problem is that Planck sees and baryon acoustic oscillation, the best fit point on the mass is negative. Okay, this is what's happening. 80% of now if you include DESI, the situation becomes worse. This is 4 years old. I put this plot, I chose this plot and not the new plots to show you that this is a long-standing problem we have in Planck. So 80% or 85% of the region is on the unphysical side. Does may mean that I believe neutrino masses are negative? Of course not. I don't believe that. Okay? So, no. The thing is that for me, this is my take on. There is something going on there. Okay? Some people like to think that this is dark energy non-being constant. Okay? So have a quintessence field. This may be some kind of other physics. There are a lot of kind of physics. For me, the take is that the 6-parameter lambda CDM is an oversimplification. And okay, so your feed is a feed. So it will do the best it could. I mean, so you are getting a feed in the negative region. So you have to think what are the ingredients you put on that. Okay. So this is the closest you can get with these parameters. This means that you are needing one parameter more or maybe something different. Remember, if one warning for that, you cannot reproduce these bounds using the standard MC and CIS. Do you have their class and camp? You cannot do that because they force your masses to be positive. So watch out what you are seeing. Normally people, I commented this yesterday, hack the codes and change the lensing potential to get these plots. You have to be very careful what you do. You can do whatever you want, just know what you are doing. But in any case, these, together with the gallium anomaly and with many other things, means there is something going on where neutrinos may have a say. I'm not saying they are gonna have a say, I'm saying they may have a say. Okay, so after talking for almost 3 lectures, 2 lectures and a half about mass difference and absolute masses, we can discuss finally what a mass is. Okay, so I said by passing yesterday that the mass can be thought of just as the left-right interaction. Okay, you put your left-handed doublet, you put the Higgs doublet, you put your right-handed singlet, your Higgs doublet acquires a web, and voila, your fermion has acquired a mass. Okay, but if you like to think, I like to think about it in terms of the components of the spinor we saw in the very first lecture. If you think about the components of the spinor we saw in the very first lecture, we know that mass connects you vertically. A mass term connects a left-handed electron with a left-handed electron with a right-handed electron, or a left-handed positron with a right-handed positron. And remember that CPT was connecting you horizontally. It was transforming a left-handed electron with a right-handed positron, or a right-handed electron with a left-handed positron. However, if I'm saying to you that the mass term is just a left-right interaction, you may ask yourself, why not to couple a left-handed electron with a right-handed positron? This is also left-right, okay? You would say, no, no way, you will never do that because this violates electric charge. And then what would happen if your particle does not have a charge? Okay, this will violate this U1 number we forced by hand yesterday in the very beginning. So what? Okay, so there are two ways. In the case, if you want this term not to be violated, you have to protect it somehow, gauge it, okay? And you have new physics associated to that. But if you don't want to impose this symmetry because you have no reason to impose this symmetry, remember that lepton number is an accidental symmetry in the standard model, then for neutrinos and only for neutrinos, you have the possibility of two mass terms. We saw this yesterday. We have the Dirac mass terms, which connects you vertically, which a mass term that you share with all the other fermions in the standard model, but you have a new mass term, which is a Majorana mass term, which is unique to neutrinos, okay? And if you want to know now what are the propagating states, which are the asymptotic states of the Hamiltonian, all you need to do is to put all the contributions together and diagonalize this, okay? And if this mass is much larger than the other two, you get one heavy state proportional to M, to the new M, and you get one term which is suppressed with the other ones. We saw it yesterday, Stefan talked about this yesterday. This is the seesaw mechanism. But the consequences of being that shouldn't be underestimated. First of all, one way or the other means you have physics beyond the standard model. You like Majorana neutrinos, of course you have new scales and new physics associated with this scale. You don't like Majorana neutrinos, fine. Then you just gauge your lepton number or protect your symmetries somehow. We know that global symmetries are gonna be broken by quantum gravity. We already know that global symmetries get broken. So it's not gonna be conserved. You have to protect it somehow, and this means physics beyond the standard model. And of course, these Majorana masses are welcome for something else, and you discussed this yesterday. You are going to discuss this in detail today, so I'm not going to enter into that. But the idea is that neutrinos can explain the baryon asymmetry of the universe. You know that the universe we live in it's matter-antimatter not symmetric. Of course, you can say, okay, the difference between matter and antimatter, you blame it to the initial conditions. You say this is the way it's created. But we are a little bit more elegant than that. We would like to think that the universe was created matter-antimatter symmetric, and this asymmetry was dynamically generated. What would it take to generate this asymmetry dynamically? Sakharov worked out these conditions in the 80s. You need C and CP violation, you need baryon number violation, and you need departure from thermal equilibrium. You need departure from thermal equilibrium because you need whatever asymmetry you created not to be restored. And baryon number is anomalous in the standard model with and without massive neutrinos. And we have seen in the standard model, you have C and CP violation. So in principle, in the standard model, you have all the ingredients you need to generate the baryon asymmetry of the universe. The problem is the numbers do not work. The electroweak phase transition is not first order enough. It's a crossover at most. Okay, but even if it were not the case, the Yarslock invariant is killing you. You don't have enough CP violation. For quite some time, people entertained the idea that supersymmetry existed and was in thermal equilibrium at the electroweak phase transition. Okay, the superpartners were in equilibrium at the electroweak phase transition in such a way that you have enough bosons in thermal equilibrium at the electroweak phase transition. You enhance the order of the phase transition. You have new phases. Voila. You open the window for electroweak baryogenesis. I'm not sure. I'm not going to enter into debates in this respect, whether people think or not think that supersymmetry exists. But what is sure is that superpartners are not in thermal equilibrium at the electroweak phase transition. So you have no way to generate the baryon asymmetry of the universe at the electroweak phase transition. However, Majorana neutrinos have its own phase transition, the Majorana phase transition or the right-handed phase transition. And of course, Majorana neutrinos are leptons. They are not baryons. They cannot generate a baryon asymmetry, of course, but they can generate a lepton asymmetry. And this lepton asymmetry, you are going to see this with Stefan, I'm not going to enter that, but this lepton asymmetry, whatever you generated, can be transformed into a baryon asymmetry by sphalerons. Okay, at the electroweak, when the sphalerons get out of equilibrium at the electroweak phase transition, a sphaleron is just a saddle point in the potential. It's just if you have two degenerate minima or quasi-degenerate minima separated by a barrier, the path between the two minima is a sphaleron. This is a non-equilibrium state. This is why you cannot draw a Feynman diagram for a sphaleron, okay? So you are going to see that, but in principle, neutrinos can explain the baryon asymmetry of the universe, and we also have seen yesterday there are several ways to implement neutrinos, and they differ on the content, on the matter content of your model, where you want to include extra doublets or extra triplets or just fermions. But there are several ways to impose the seesaw mechanism in your model and make your theory UV complete. However, and although we have heard this yesterday, I say it myself, and if you run a poll, everybody will agree with that. We say that we believe 99.99% of the neutrino community is convinced neutrinos are Majorana particles. And we say they are Majorana particles. You are not? Okay, so 99 only. Okay, I think I am Gnostic. Anyway, but people will tell to you that neutrinos have to be Majorana particles because this is the natural way to explain why neutrinos are much lighter than the rest of the fermions. So let me play a devil advocate and say you that this thing that is there, it's called platypus in English, ornitorrinco in Spanish, and I was told ornitorrinco also in Italian. This is a mammal which lays eggs, which by definition mammals don't do. Okay, this thing lays eggs and lactates, which things mammals don't do. Mammals either lactates or lay eggs. So the lesson to learn is that it doesn't matter which categories you use to describe nature, it should not be satisfied by nature itself. So the question whether a neutrino is a Dirac or Majorana particle, it's not an aesthetic question. It's not to do with whether your Yukawas are small or 10 to the minus 12 or 10 to the minus 16. It's a thing that you have to go and ask nature. So the question is how we are going to find out whether neutrinos are or are not truly neutral particles. With truly neutral particles, I mean a Majorana particle. Why I'm saying that a Majorana particle is a truly neutral particle? Because we have seen already that if you go from particle to antiparticle, what you are doing is switching the sign of all your quantum numbers. Is after switching the sign of all your quantum numbers, you end up where you were, this means all your quantum numbers are 0. Okay, so you have a Majorana particle. If after switching the sign of all your quantum numbers, you end up in a different place where you were, this means you have at least one quantum number, lepton number most probably, that it's different from that, and your neutrino is a Dirac neutrino. So I'm gonna show you an experiment which does not work, but pretty much explains you why no experiment is gonna work and what do you do to make this work. First, we are gonna assume that you have a pion at rest, and my pion decays 99.99% of the time to a muon and muon neutrino. And this by itself already teaches us volumes, because if you think about that, a muon, I'm saying a muon decays to muon and a muon neutrino. However, if you think about this is really makes no sense. You should decay to electron neutrino, phase space. It makes way more sense to decay to electron neutrino to a muon neutrino. Come on. I mean, this is 140, this is 100. The electron is half. So what's going on? Why I'm decaying to muon 99.99% of the time and not to electron, which should be a no-brainer? You know the answer. The answer is, if it's not kinematics, it's dynamics. I mean, physics has two answers. Okay, so this is not kinematics, it's not phase space, it's dynamics. It's because I have to make, when a pion decays, I'm making a left-handed neutrino, but therefore, for this has 0 angular momentum, for angular momentum conservation, I'm making a left-handed antiparticle. And we know that nature does not like left-handed antiparticles, weak interactions. Weak interactions like right-handed antiparticles. So you have to pay. Now, helicity and chirality are not the same thing. Helicity is not a good quantum number any longer. You have to pay the helicity price, and this is why you produce a muon and not an electron. Okay? This is an exercise once in your life you should do it, because it's a very, for me, a very educative exercise. So we are going to produce, let this pion decay at rest. This pion will produce muons and muon neutrinos, but I'm going to now boost my system. I won't let my pion decay not at rest, but in flight. So every particle will be moving forward. The velocity of the pion in the lab should be larger than the velocity of the neutrino in the pion rest frame. I should be able to reverse the direction of motion of my neutrinos. Now I'm letting my pion decay, but in flight, with so much momentum that every particle is moving forward. Okay, and then that's it. Now I have transformed my left-handed neutrino into a right-handed neutrino. And if in the standard model, right-handed antineutrinos can produce positively charged muons, and the neutrino is a Majorana particle, meaning that the neutrino of a given helicity is the same as the antineutrino of the same helicity, then if my right-handed neutrino is identical to a right-handed antineutrino, then my right-handed neutrino should be able also to produce positively charged muons. So the experiment cannot be more easy. I boost the pion, let it decay in flight, and just wait for the muon, a positively charged muon, to appear. Okay, there are some technical difficulties with that. We put only one condition, and therefore the difficulty is only there. Let me say, we say that the beta on the pion in the lab should be larger than the beta on the neutrino in the pion rest frame, okay? This is what we said. This is the only condition we put. The rest was done. But beta, remember, beta is P over E. And if my particle is extremely relativistic, this is 1 minus m squared over 2e squared. This will mean that the beta of the pion in the lab, 1 minus m pion squared over 2 times the energy of the pion in the lab square should be larger than 1 minus m neutrino square, 2 times the energy of the neutrino in the pion rest frame square. Okay? So you can remove this and just switch the sign here. This means that the energy of the pion divided the mass of the pion should be larger than the energy of the neutrino divided the mass of the neutrino. Okay? Squares, but this is the same. Okay? This is just putting this here and this here and suppressing the two. Okay? This is, but remember that this is in the lab and this is in the pion rest frame. And we have calculated yesterday that if I have a two-body decay, like this one, this is a two-body decay, this is pion going to mu, mu, the energy of this neutrino is completely determined in terms of the masses of all the particles involved. We calculated this explicitly yesterday. Okay, so I can do that. And if I plug numbers in and I put an absurdly large neutrino mass, a mass of 1 MeV, which I already know it's at least 1 order of magnitude lighter than that, the energy I need in the lab is 10 to the 4 TeVs. So it's a little bit challenging, but it's not only that. It's the real problem is that now neutrinos are not massless. Helicity is not a good quantum number, it's not chirality any longer, and I have to pay the price for the helicity flip. And the price for the helicity, you know it, is m over e. So even though if I were able to reach these energies, the fraction of all this, the pion decays that get helicity flip will be m over e suppressed. So although in principle this is perfectly allowed, is suppressed by the mass of the neutrino over the energy of the neutrino square. So you already know that this is the factor I need to beat. So this field is called high energy for a reason, because we have high energies. So with the energies we have, we are not going to make it. So we have to now abandon, if we are trying to target this, we have to stop doing high energy physics and join forces with those people we have been blaming yesterday for all our problems, the nuclear people, okay? We have to stop, because in nuclear physics, you have the energies you need to see that, and this is why we are going to see that, okay, by doing nuclear physics. How? There is a known process which is called two neutrinos beta decay, where simultaneously inside the nucleus, two neutrons become two protons, emit two electrons and two antineutrinos. So if you measure, so in principle you have 6 bodies in the final states, okay? 2 protons, 2 electrons, and 2 antineutrinos. However, if you measure the recoil of the nucleus, the combined momentum of the 2 protons, this counts as 1. You measure the combined momentum of the 2 electrons, counts as 1, but you still have 2 antineutrinos. So this is effectively 4-body process. So you know the spectrum is continuous. So you know already that in 3 is continuous, in 4 is also continuous. However, if the neutrino were a Majorana particle, there is a possibility that the antineutrino emitted in one decay get absorbed as a neutrino in the subsequent decay in such a way that you end up with what is called neutrino-less double beta decay. So you have a double beta decay with no neutrinos emitted. Okay, so if you do the count we have done before, you have the recoil of the nucleus, the combined momentum of the 2 protons, plus the combined momentum of the 2 electrons. This is a 2-body decay. So the signal should be a delta. Kinematically, should be very easy to distinguish one model, one decay from the other, and this is the process we are searching for. And of course, we already know this process is going to be proportional to the mass over the energy, because this is what we are targeting. But notice that contrary to all the process we have seen so far, this is not the sum of the absolute value of the matrix element square, as what we have seen before. This is the absolute value of the sum of all the masses times the mixing matrix element square. So this means that the Majorana phases, which were not present before, are going to show up now. But this comes as no surprise, because I said before that these phases will show up in a process where neutrino is forced to show is the Majorana particle. And this is effectively one of these processes. If you expand this term in its component, this is what you get, where delta is the Dirac phase, and you see the two Majorana phases, the two phases appearing here. So now this is the m beta beta, the effective mass you measure, and you realize immediately that whether your spectrum is normal or inverted, it makes a huge difference here. Because if your spectrum is inverted, remember the difference between normal and inverted, whether it was whether M3, the state with the smallest electron neutrino content, was the heaviest or the lightest. In inverted, M3 is the lightest. Okay, this will mean that this mass is the smallest mass. Is the smallest mass and comes with the strongest oppression, with a reactor mixing angle. So this term is negligibly small, it's miserably small. So you have only these two terms. And these two terms are identical, except that one has the cosine of the solar mixing angle square, and the other one has this sine of the solar mixing angle square. But the solar mixing angle is not pi over 4, is close to pi over 6. So this means that no matter which value takes this phase, there are no cancellation possible between these two terms. It's not possible to have any cancellation, no matter whether this is a total minus sign. This will not cancel totally. So if the case, if you have inverted spectrum, then you are bound to have a signal. If you have normal spectrum, then this is the largest mass and come with the strongest oppression. So the three terms end up being in the same ballpark. And you can play games in such a way that you choose your phases in such a way that at the end of the day, you can cancel the effective mass. So it may happen that nature, who has been incredibly generous so far, may be mean this time. And maybe neutrinos may end up being Majorana particles, but phases are such that we end up not being able to detect neutrino-less double beta decay, although being neutrinos Majorana particles. And of course, the dividing line is here. So now if you assume, that all the only process contributing to this neutrino-less double beta decay is just this effective mass, you can put bounds on the effective mass using the half-life. This is how you measure that. You put your nucleus, you sit and wait for this to happen. You don't see that, you put a bound. Okay, this is how this works. These are the bounds you have been getting, and if you translate this to your spectrum, this is what you get. Okay, so again, you see that the inverted spectrum is about to be ruled out. So we are pretty sure for different places in physics, that is, neutrinos are normal ordered and not inverted ordered, but maybe, you don't need more than 1 point in parameter space. So maybe it's here, your spectrum. So we don't know. We don't know. Okay, so it's my time. Let me start concluding. First of all, the message to take home is neutrinos are aging well. The neutrinos are fantastic. For those of you who think neutrinos are the new thing, you cannot be more wrong than that. Neutrinos are about to turn 68 years old, okay? Neutrinos make true what we would like to be true for other parts of life. For neutrinos, the 60s are the new 20s. Indeed, neutrinos are with 60s way more sexy and way more interesting than they were when they were 20 years old, okay? Unfortunately, this is not true anywhere else. But at least we can do neutrinos. Okay, so neutrinos are the third oldest particle in the Standard Model, the electron neutrino, of course, younger only to the electron and the muon. So the fact that there is all this hype with neutrinos has nothing to do with them being new. Neutrinos are becoming more interesting as time goes by, and this is not happening to the rest of the particles in the Standard Model, but neutrinos are quite old. And this is why we shouldn't stop being excited about the new and interesting things that are to be done in neutrino physics, okay? Neutrino physics was, I said this yesterday, was not even a serious thing to do. I mean, not that long, 30, 40 years ago, you know. I did my PhD in flavor physics because my PhD advisor considered we were doing neutrinos. We're not serious enough to land you a job, okay? So, but this is true. I mean, I landed a job, so he was right at the end. but what I'm saying is now we have a dedicated school to neutrino physics, many of them. This was something unthinkable of 30 years ago. Now, this is the exciting news. Now, the technicalities are we have been doing a very successful, I mean, short and long baseline program, and we were able to nail down the mass difference and the mixing angles of the neutrinos to an amazing extent, okay? We know the two mass differences, we know the three mixing angles, we are pretty sure we know their values with different accuracies, of course, remember that. We still have a long program ahead. So we think it's normal ordering, as I told you, and not inverted ordering. We still have things to do. We need to know about CP violation, of course, not only the ordering. And also some people are very interested in the octant problem, whether the atmospheric mixing angle is slightly higher than pi over 4 or slightly smaller than pi over 4. For making a comparison, this is where we are. This is where the quark people are. We are still far from the precision they have on the CKM matrix. For quite some time, we entertained the idea that getting precision on the CKM matrix elements will shed some light on the flavor problem. I'm not sure whether this is true, but at least we need to give it a try. But of course, we don't only need precision. We have a lot of things we would like to cover in the coming years. First, and the most important thing is we need to know whether neutrinos are Dirac or Majorana particles. If neutrinos are Majorana particles, this will be the first Majorana fermion ever. We have no Majorana fermions, no fermions who have the chance of being Majorana other than the neutrinos. We would like to know that. We may have or not light sterile neutrinos. As I said yesterday, I would like to emphasize today, we have no reasons to have sterile neutrinos. We have no anomalies to accommodate. We do have anomalies, but most likely than not, these anomalies are not related. The gallium anomaly for sure is not related to sterile neutrino. There is something going on in cosmology as well. It's not related to sterile neutrinos, but they still may be there. Remember Isidore Rabi said when the muon appeared, who ordered that, okay? So we don't know. So we just have to go and look. Of course, we would like to know the mass hierarchy, whether M3 is the heaviest or is the lightest, whether CP is or is not violated on the leptonic oscillations, and we would like to know the mass of the heaviest neutrinos, and of course, we are open to new interactions and surprises, and we are not standing still. We are doing an innumerable amount of experiments over all the baseline lengths, over all the energies, so we are bounded to find something in the next coming years. Thank you. Any question? A comment? No? So I can comment on you, how do you implement CPT? CPT technically, okay, so if you want to implement CPT, technically you have to violate, I mean, the way I implemented that is it through non-locality. You have to be very careful in doing non-locality because you don't want to violate causality. But you can do that. You can do that. I mean, I have a series of works together with Joe Licken showing how you can do that. You can have CPT violation. You can have CPT violation with Lorentz invariant also. So there are ways to implement it. But remember that, I mean, for me, when I was doing that for first time, it was a journey in the sense that we are so used to work and calculate inside the framework of local relativistic quantum field theories that to go out of that is very difficult. It's very difficult. No, no, this is, yes, this is just a phenomenological approach. If you are trying to do that from the formulation, some people have done that. I think Nick Nabromat. Yes. No, you are not using the same rule. I mean, in the case, you are looking for this into oscillations. And remember that in oscillations, you are using quantum mechanics. You are not using quantum field theory, except for the detection. But the detection is pretty safe. Remember that oscillations, you are using quantum mechanics, not quantum field theory. So you are pretty safe in this respect. So I would say that this is not a problem for that. I mean, you can have problems when I'm saying if your theory violates causality, you may have run into problems with that. But I don't think you can run into problems if you look for this into oscillations. I don't think so. Anyway, so we better go to the coffee break. Yes, of course. I don't object that. What I'm saying is what you are testing is whether QCD respects CPT or not. You are not testing whether elementary particles. Yes. No, no. Okay. No, no, I said it comes from QCD. It does not come, what I say is not come from the quarks, the elementary particles inside, but from QCD. But then what the only thing I'm saying is that you are testing that QCD respects CPT, and I have nothing against that. Fine with me. What I'm saying is, does nature respect that? Which is a different question. So the theory you use to describe it has CPT built in. Fine. I'm not saying not. Local relativistic quantum field theory also. But I mean, for me, the testing CPT is fundamental in elementary particle system because it does not test our model. It really tests the tools with which we construct models. It tests local relativistic quantum field theory, and in this way, it's way more powerful than that. It objects the way we construct any theory, not just this one. And this is what I say. But I mean, I have no objection with that. No, what I said that if you include DESI results, DESI are baryon acoustic oscillations. So DESI, you cannot analyze DESI by itself regarding neutrino mass. You have to anchor DESI results with Planck. So if you do the combined result, DESI plus Planck, the sum of the neutrino masses, the 95% confidence level bound on the sum of the neutrino masses goes below it goes around 0.07. This is what I said. But the only thing I said is the problem is not DESI itself. This is a problem Planck already had for 4 or 5 years. Okay, this is not related to DESI, and because people object DESI for many reasons. Okay, but this is not a problem related to DESI. Just you can throw away DESI and this result won't go away. What is happening is that you need all the baryon acoustic oscillation results, or supernova result for that matter, need to be anchored in some way to get to run your Monte Carlo, to put a scale, whatever. And this means you have to use Planck. And Planck plus this data give the sum of the neutrino masses, 80-something% of the parameter space is unphysical. Okay, so when people show you, this is what I'm saying, when people show you this bound for the sum of the neutrino masses. What they are forgetting is this. You are just seeing the tail of the Gaussian. And nobody expected, what I'm saying is that we all expected. This is a fit. So if this were near zero, I think nobody will complain because it's something you expect, okay? I think it's striking that over the years, this is only getting worse. In fact, Deci and other, Planck by itself, I show it, Planck by itself is further this side. It's baryon acoustic oscillations, all of them, which is throwing them this side. These baryon acoustic oscillation experiments narrow the Gaussian and push it more on the positive. Planck, it's true that it's more spread and on the negative. So, in fact, Deci is helping us, but helping us narrowing the Gaussian also makes that most of the unphysical region ends up being on the negative. But this is good, people, because this means there is something to learn there. Neutrino masses, negative neutrino masses are just a proxy for something we are missing. It's your work to go and see what we are missing, okay? You have a lot of competition, though. If not, let's go get some coffee.